What's up? All right, finally getting onto being live. Almost getting this down, except for the fact that I sometimes just forget how to work all this stuff. Where's my OBS? So I hope everyone has had a good, wonderful week. My week has been great this morning. Not quite so much. I don't know if you caught the community post, but it definitely has been a morning that I have wanted to, I don't know, start my weekend early. Maybe go on a vacation to a beach somewhere. I don't know about you guys, but I normally am not a beach person, but my wife definitely is a beach person, and she introduced me into this thing called uh what was it called? Called being relaxed. Oh yeah, that's what that's called. I kind of forgot about it. Um yeah, that whole being relaxed thing, just sitting on a beach, sitting there listening to the waves roll in. Yeah, not 25 degrees in the South US, which miserable. I know all if there's anybody from like the Midwest or like up north, like y'all are sitting there saying that I don't know what cold is. You have it's a dry cold, so it's less miserable. And I also want to point out, um, don't don't like get into arguments with inanimate objects because they always win. See my nice little thing. Yeah. Started off this morning trying to go take a shower, and the closet door just didn't want to allow me to do that, so it won. It was an argument, it was a fight, but we're all good. The door's fine. I'm fine. I just want to start the weekend. So we're getting a little festive, a little island time here. And yeah, so today we are going to be talking about, once again, my favorite subject, Siemens drives, particularly S120s. Had I had a viewer that asked a comment a little while ago. Actually, it wasn't too long ago. It was last night, I do believe, that they made a comment asking how to connect up some stuff with some S120 drives, getting some contactors going. And so that's what we're going to do today. We're going to start off this thing by jumping into Portal version 17. And yes, yeah, Michael, yes, call that's it. Awesome. It's great to see y'all here. And Lucid, yes, the door is okay. Um, yeah, I the door is perfectly fine. And so we're going to pull up the other screen, and we're gonna put me here. And so what we have here is our drive system from actually the last couple of weeks. Like, we've been kind of building off of this program, and yeah, we are going to add in a feature because Michael that's in the chat today, he had a question about controlling a contactor with an S120, and it's probably a little known thing because we talked about interconnections, BICOs, and things like that, and you may not be familiar with the S120 system, that it does have a little bit of I/O in this in the CU 320-2. So there's a little bit of built-on I/O, and then you can have an expansion card on it. And what Michael's request or question was how can we get a contactor control for this, so that when you turn on the drive, or that you're not having to manually turn on the contactor. I think he said that he was turning it on in start drive, to just manually turning that on. And one of the things that in start drive, I've noticed that it kind of doesn't really fully show it that well, but if you're using Starter, the older software, it had a nice little page for what's called contactor control. And the S120 drive system actually has contactor control built into it, and it has logic that's always running that will allow you to be able to, like when you enable your drive, you can set it up to where the contactor will come in and close, the precharge will come up and go. So I'll show you a simple way of doing that. Last week we talked about connecting up some Byte parameters for a free telegram. But I wanted to show you first where the IO is in the CU. So our control unit here is named drive control, and underneath parameterization, we can bring up all of our parameters, and these are also available in function view as well. Let's bring this up, because if you look over in the left hand tree over here, you could see inputs and outputs, and we're going to want to use the bidirectional digital input and output. So this is how we're going to control our contactor. And if you're not familiar with what it's meaning by bidirectional, you have this little bit here, and for Michael, I think he said that he was using DO9 for his contactor control. And you could think of this side on this left hand side as the actual terminal itself. And because these can either be inputs or outputs, there's this little switch here to control whether it's an input or output. And the way you think about this is you can see these little arrows. This is currently set up as an input, so you would see the input come in from the terminal, come into the CU, and we're going to first want to switch this over to an output so that it's coming from the CU out to the terminal. And now this is just going to be a 24-volt signal, and so depending on what type of load you have on this, like you may want to use a relay, and so that is that. A couple little more things on this little block here is an invert, and so if we were actually online right now, we have a 0 signal coming in here that's connected to the BICO connector here. If we were to invert that signal, this output would actually come on, and that may be how Michael is turning this on and off. But if not, there's a signal there to where essentially you would be able to, whenever this CU comes up and powers up, you could just have this 0 signal, invert it, and it would automatically turn on once the CU comes up. So Michael, that's your first option. You can hard code that there. But we're going to look at a little bit better option. We're going to turn that off, and we're going to go into one of our drive objects. Now, one thing to note is that in our S120 system, we kind of talked about it. In a common DC bus system, you have a line module or an in-feed, depending on what you're calling it. By default, they're called in-feeds in Siemens land. And then you have motor modules. The in-feed module turns on and creates a common DC bus for these S120 common DC bus lineups. And then the motor modules are actually just inverters, so they are DC to AC converters. So in these S120 systems, most of these line modules have a what's it called? A telegram themselves. And so you can see here we have a telegram right now. I was playing around with this, so I kind of undid what we did last week. And so it has its own telegram. It can even have its own extension, all of that. So there's a drive click cable going from the CU over to this line module. Now, the reason I bring that up is this is an active line module, and you have to turn it on and off itself. And all of the contactor control functions are available in the line module as well. But the S120 isn't always a common DC bus setup. So you can have kind of chassis style units, or you could even have a CU310 that's on a G120 power module that you could actually use this on. So all that to say, the parameter numbers that we're going to be working with are the same in a line module as it is for a motor module. And for that, we are going to be looking at parameters 860. So I have pulled up our following axis here. And again, I was playing with all this earlier. So make sure if you've been kind of messing with stuff and searching around in the parameter list, that your parameter text says all, because I can sort, and this is, you can sort by you can see where I've done this earlier, and you can kind of bring up all of these other functions or all of these parameters that have the word contactor in them that way. Well, now parameter 860 probably has, well, it doesn't, so, well, it does, so it would pull up in this. But if I were to go to like so our P10, if normally you would be able to click in this number and you would be able to just type 10 and it would go to it. Well, I typed 10 right there and it did nothing, and it's because parameter 10 does not have the word contactor in it. So make sure that this always says all when you're kind of searching. Now if I click here and type 10, it'll pull up parameter 10. But just a little trick, we're wanting to look at parameter 860, and again, I think Michael said that the parameters, or he was using starter, so looks a little bit different. Honestly, it has its own little page in the like graphical page, whereas in start drive it does not have a graphical page. And so I'll explain, I might even pull up starter here real quick just to show you that page, because it kind of makes a little bit more sense. So what you have is actually, let me just go ahead and do that, because the parameters are the same, but there's just no graphics, and I'll show this to you. All right, so what I have here, pull this up here, is a starter program. It's a winder that we have, and it's an S120 system, and it has just all the same stuff, but it also has a contactor, whereas some of our stuff don't always have a contactor. So this would be under one of the drive units itself. CB20. Okay. So Michael's explaining a little bit more about the system. And so he says, starter, because I also use CB20. I have Profibus CU. I'm not able to use its start drive. Yes, that is correct, Michael. So he's using the CBE20, which is an expansion board for the CU320-2, and currently, apparently, the current version of start drive does not have the functionality to be able to connect using the CU320. I'm sorry, the CBE20. And so, yeah, so that's a good reason to do that. But that CBE20 board is pretty cool. I wasn't aware that it wasn't in start drive. But let's look at this contactor. So we have this under a drive object here. So this is a drive. It's an accumulator drive, and we're gonna go underneath functions. So functions, line contactor control, and it brings up this page. And again, I'll repeat it multiple times, same parameters, but what this is doing is this is a built-in function that is actually always enabled. It is always monitoring this contactor. It's just that by default it's set up in a loop. And so what this is doing is this line contactor control is our 863-bit 1 energized contactor goes out, and that's the signal you're going to want to tie to your D09 in your case, Michael. And then this feedback this checkback signal, if you have auxiliaries on your contactor, then you would want to actually bring that into an input, and just to make sure that that contactor actually is closed, because there could be some issues if your contactor is not actually getting closed, or if it's not completely closed and you try to load down this system. So that's what this is built in as. And so we have this line contactor kind of enable circuit that is actually controlled by the status word. So when you try to turn on this accumulator drive, this will actually power up and go through. And as long as you have it bypassed like this, then there's no real, like, I guess there's no way it's going to kick you out. If you don't have the output to your contactor and then the checkback or the feedback signal within this 100 milliseconds right now by default, then it will give you a fault that says line contactor checkback missing. And so it'll actually give you a fault that'll keep you from running if you don't have this set up correctly. And most of the time, if you actually have a real system, 100 milliseconds probably or maybe isn't fast enough, especially for a big contactor. So that's kind of the first place to check if you were looking and you're getting these line contactor checkback signals. So to kind of get not to belabor this too much, this line contactor control, we want to set this to our that is not how I want to do that. We want to set this to the actual bit that we're using out in the world. So this is input coming back in, and so this is going out. So we would have to go over here, look at our control unit, see where this actual input output is, and DI. So different for the DI09 output here. I want to set this to in this one it would be this under drive unit 2. Alright, so what I just did there is I opened up the wrong CU. We have 2 CUs here. So we're going to pull this up, bidirectional DO, that there, click here. We're going to connect this to accumulator, and it should, as this is one of the common things, not quite. So we're going to go to further interconnections, and we're going to go to accumulator. There should be a place for 863.1 right there. So now that contactor control, anytime that it actually pulls in, it's going to send out that signal to close the contactor. Now, the way this is set up right here is it's still bypassed. The feedback is still bypassed. And so you're connecting this R863 is getting connected into our P739, and I'll show you how to do this in Portal as well. But that's the actual official contactor control method of doing this, and it's all built into the drive itself. So just Michael, on your system, that's probably going to be the best way to do that. Another way that you could do this would be, like I said, a kind of a cheaty way to do it You could just set this to be either always on, and so whenever the control unit comes up, it tries to close that contactor, but then that kind of doesn't really give you a way to do that, or to kind of turn it on and off. Or if you have, I don't know, Michael, if you type in the chat like what telegram you're using, that would help me to be able to go from here, because in most of your status words, even if you're using a 105, okay, so let's change that to do, so I'll show you Michael how you can turn it on with a PLC using that 105 telegram. Let me set this up real quick. So I don't have that available, but because this is a vector drive, so I will need to go up here because these are the servo drives. I know Lucid might find this program familiar. But let's see. Do it on this. Do communication. I'm getting my screen is cluttered. So in your status word, here, so this is receiving from the PLC to the drive. Your standard status word for almost every telegram is going to have a couple of these bits that are available. And so what you can do, Michael, is go through and connect one of these bits into your control unit CU DO/DI9 signal source for terminal. So you can go through and connect that, and now you would go through and bit, so that would be, technically that would be if you're just sending a word out because of the byte swapping that's going on. Yeah, so good point there. With your CU as a different telegram than the drive, it doesn't really matter where you send it over. I normally would send most of this stuff, like you said, over to the CU, but even if you just have a drive, you can send this data over and control it through the CU. Like if you don't have your CU set up for a telegram, you can use this bit 8, which would be in your actual word, would be 0.0 because of the whole byte swapping thing. So it would be whatever your output here would be that. And so what's interesting is that like locked in once I actually set that. But yeah, so we have set up here, you could go in and these free interconnections here, you can actually set those up. And let's see if I can go undo that on the other side. I don't mean to spend a ton of time on all of this, but you can see here that signal is now coming in from the apron and going there. And so if I wanted to disconnect that, I could say 0, and I should be able to come back over here, and there you go, it's back available. 840 is 840 the 840 is the in-feed enable bit, correct? So so let's look at the 840, I believe, is Yeah. So 840 is the on and off. And so like in that communication telegram, go back to it. 840's set, and it's you can't reconfigure that because your telegram is going to have that locked in. The only way that you would be able to modify that would be if you change this to a free telegram, and then it would allow for you to change it there. So you, let's see, I guess you could do it that way, but you could tie this control unit to, like you said, say like an apron 840, and that would be kind of that drive enabled. Actually, it doesn't even look like it'll let you. So, because that's yeah. So sometimes, let me see one other thing. You may actually be able to do the 2090. Yeah, so you could go through and set like bit 1, and so that's there. And then now if you go back to this, it'll show multiple, which I didn't get the right one, but it'll show multiple. That one telegram bit actually gets connected out into multiple places. I would advise against using it's funny because I actually tied it into the off 2, which kind of would be the same thing. If you lost your off 2 signal, you would want to close off your essentially off 2 gives you kind of an STO, so it makes it to where you can't generate torque. So the way I accidentally configured it right there using bit 1 instead of bit 0, you could use that. I wouldn't use the off 1 though, simply because the delay that it takes for everything to kind of, the contactor to come in, the pre-charging to come up, the DC link voltage to come up, you might run into problems and faults with saying that the DC link is not ready. And so I personally would put that into a into one of the other bits. Yeah, Lucid, it exactly. I mean, and if you're, Lucid brought up the fact that if you're not using like your CU telegram, for example, if you're not doing anything with it, you can add in all of these bits for contactor control. Maybe you have some like running lights and stuff. Like you can definitely add those into the telegram going to the CU. And that was in the last live stream that we did. We talked about that, and I just worked this morning on getting everything clipped out to kind of detail that out. So maybe by the end of the afternoon, the video specifically about making a free telegram in your CU will be up later this afternoon. But that's what Lucid's talking about with setting up a custom telegram to your CU, that you don't have to kind of mess around with all this stuff in your drive CU. You can use just a standard configuration drive telegram. But yeah, I personally would want to have individual control over my contactor, so that I could turn that on inside my PLC. I could send out, all right, turn on the contactor, and then wait, say 2 seconds or so, just to make sure everything's up to voltage and everything, and then allow it to run. Which, that brings up one question. Let's bring up this, because there is a 864, and so parameter 864, I don't know what it is actually is configured to, like in your system, but this is the in feed in operation bit. And a lot of times this just gets turned on to a 1, but it shouldn't be. It really should be some way of telling whether or not the DC link voltage is actually up to speed, because if you start loading things down while pre-charging resistors are in circuit, like there could be some issues there. So, and you definitely want to tie this parameter 864 to something that really actually signifies that the DC link voltage is up to voltage. In this particular project, that signal is generated by the line module, and it automatically does it here. So that's why you can see that the line module 863.0, that's just the status off of the line module that was it's ready to go. And 863.0, what are the odds? That's from the contactor control parameter set. I think that's pre-charging complete, if I remember correctly. But yeah, so let's go just real quick as a reminder back into for the that should explain in starter how to do that. Your options, a couple of different options there, but it's all based around that parameter 863.3, or using 863.1, or using kind of like you're wanting a free bit in your telegram to be able to connect into that. So let's show real quick. Bye bye starter. Starter is my first love. Yes, I'm weird. Don't judge. So we go over here and we can look at parameter 860, and 860 is going to be the feedback signal that we saw. And really there's only 3 parameters for this line contactor control. There's parameter 860, which is the feedback. So right now it's bypassed. So whenever our enable energized contactor signal comes on from the contactor control, it just feeds right back into it. You have the line contactor monitoring time, and that was the thing that was built into the kind of like function in starter. That's just how long it's going to wait to see that feedback signal. Power unit on delay is when you get the so that's you give it the signal, how long you're going to wait in order for you to send out the signal to turn on the contactor. That's what that delay is. And as you can see, this 860.4 or 864 is this that in-feed in operation, because all this is about getting your DC link voltage up to speed. But yeah, so here in start drive, you'd want to go over to DO9, set it up like we have here, click the Byte parameters the same way. And if you were using, we'll say like Lucid suggestion, just a bit from our Profi drive, so PZD1, which would be the status word, let's use that bit 8 that we said before, so 0.0 that we set up in starter. Let's just connect up that and see if we can go see that. So that's in drive control, and that was also in drive control, wasn't it? So we can go parameter view, communication, and then receive direction. PZDs receive 01. I'm doing this backwards. No, I'm not. And so we're connecting this R90. We're connecting that into that. It's not going to show it here, duh. So, but it's connected up there to bit 8. So when we receive that back into our drive, that's what that's going to look like. And let's look real quick because I did use that last week, so we should still have our little tags set up in our CPU. Just to real quick to show the way that we have that set up. So our CU info on system 1, and we made this little PLC data type called CU system output data, and it has these, and we've tied that to that CU free telegram. So we'd set it up last week as being output voltage, so just don't worry about that. But this is the input, so this is coming back from the drive. So I guess technically what we're sending out we haven't actually set up. So I guess we could do that real fast. PLC data type. Let's add a new data type. CU system data out. Or yeah, I name it that way. It's dumb. System data to drive. Maybe that's a better way of saying. All right, so we're gonna look at this. Let's make some bits. I'm just making one, oops, 1_0. We'll get our first word going here, like that, and then we wanted bit 8, but because of the byte swapping, we're gonna have to do this as line contactor on. Okay, so we've got that, and we've set that up. Now we can go in and make a well, we won't do this quite yet because we need to set up, at least have one. Control 5, get that up. Drive control in our telegram. But outputs. So we only have one word. So that's fine with me. That's all we need. So that is at 418. So what we're gonna do, so we have one word going to our CU. We're gonna say CU info out. CU info out to drive system 1. That's a lot. CU system 2 drive, and then memory like a goldfish 418. It's gonna be Q 418 18.0, and then that's it. So on our drive side, drive control, we've set this up. So we're receiving this in. So this is in the control unit, drive control unit. Our 2090.8, which because of byte swapping, that's going to be 0.0. And we have set up this tag. We made a custom data type, PLC data type. Yeah, so you can set this. You can set the same type of setup in for starter as well, Michael. So this is kind of all on the PLC side. So even if you're sending stuff over Profibus, everything on the PLC side is going to be exactly the same. It's just kind of dealing with that these values. So yeah, so that's kind of what it would be. So 0.8 in our CU, or .8 is going to be right here. And there we go. So that's all you need to do. You just point this output to the output address of the telegram, like we did here. And that Q418, and that's it. So that's pretty much it on this. And like, if you have kind of more questions on that, Michael, I mean, I went into setting all of this up in that last live stream, and it's kind of done like this as well, kind of relaxed and doing that. And so this is one of those things that really opens up what you could do with not just start drive and starter, but just with the S120s just in general. Cool thing about it is I believe the G120 has the same. You could do the same setup, like manually doing the outputs. Let's look and see real quick if there is the contactor control on our G120s. So if you remember, this system has a S120 system and a G120 system in it. Let's see if it has line contactor control in it. Look at that. See, it even has. Why don't they do that for the S120? That makes me sad. Siemens, oh, you got the page for the G120, but not the S120. Yes, Michael. So like, yeah, you can just build up your bits and program with the Q418, because that tag, the way we set up that tag, it has all of the bits. So like, we did this last week too, but I'll show you. Yeah, you can just go into main, and so we can go and do like a or we can do this, for example, like do like a no op. I don't think I have a no op. We'll cheat. I'm showing you all my tricks. Full faults. Bam. Now it works. So we can go in here and now go into CU2 drive system, line contactor on, and the second that works, that would come on, and so that would turn on that bit in your PLC, or not in your PLC, but in your drive. So pretty simple. And if you go through, you actually have access to like all of those. So let's just prove a point. CUTO drive system 1, because we went through and took the time to make that PLC data type and break it out into the bits, you have all of those there. And then now if I go into stat 4, we say okay, and then I go back in and change stat 4 to something cool. I may have to update this, but nah. So easily updated. That's why I use the PLC data types, because now I can even go through and behind this say, hey, I want to add in a data type of. It won't let me because the thing's restricted on the IO, or at least I hope it won't, because you could start overriding other IO. But you could do like custom set point in, and do that as like an int. And so now if we go back and look at our tag, all of a sudden all of that's updated in the tag. So oh, 47E and 47 47F. Yeah, so so that is the hex values for, I'll show you what that's doing. And that's kind of like a cheat code, I guess. So let's look. So Michael's bringing up a very good point, and I'm glad that he's going through this, because this is something that a lot of people get hung up on getting started communicating with a Siemens drive. We'll pull this up since this is what you're working in. Let's go to the communication. So what that 47, the 47E and the 47F is, 47E sets up everything but the this on-off one. So if you notice in this, yeah, fortunately we've got, there's a lot of bits that you actually just have to have on. So off 2, so bits 1, 2, 3, 4, 5, 6, and bit 10 all have to be on before the drive can even attempt to be on, and they have to all be on one cycle before you see bit 0 come on. So there has to be, everything has to be on without bit 0, and then it has to see a positive edge for bit 0. So, and one thing to note, especially for you, Michael, because this is a really big thing. If you do not have this bit 10 lit up, you can't trust anything that's on this screen. So like, obviously I'm not connected up to a drive right now, so this is just was the status of the last thing that we said, or that I uploaded from. But so apparently I uploaded when this drive was in operation, because it has everything on, including the on-off one. Bit 10 has to be on, otherwise nothing on this screen is even updated. And so whatever just the last status was, if you lose a bit 10, it'll just show you what the last status was. And so a lot of people get tripped up when they're going in and trying to get communication, and they're like, I've got all this on, but their bit 10 is not on. And they don't realize that, oh, if bit 10 is not on, the drive rejects everything that comes from the PLC. So that's what that 47E, 47F is. It's just turning on that on off. So in our back in this, bit 10 would actually be stat 2. So we would want to go into stat 2 because it's bit 8, 9, 10. And so this would be control by PLC. And I know this is for the control unit, but the same principle runs true. And so this would be the bit that you would want, because this bit comes across into the S120 system right here. So bit 0, 0, 1, 2, because these are byte swapped. And hopefully on the byte swapping thing, I probably need to I need to do, because I can't remember. I think I did one of those in one of my videos, but byte swapping is something that's a little annoying. Let's see if I can get everything up and going here so that I can show you how to show what I mean by byte swapping. That there. We'll pull this down here, doing all the things. I'll swap to this. And we'll pull this over here. Ah. All of my screens and stuff. So, when work, yes, it does. Okay, so these bits. So, in from a drive's perspective, this is byte 0, byte 1, and so in the process getting put to the PLC, like back and forth to the PLC, these get swapped, and so the PLC it ends up getting read like that. And so what happens is if you have your 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So if on one side, one is dot 0, dot 1, dot 2, dot 3, dot 4, dot 5, dot 6, dot 7, 1 dot 0, 1 dot 1, 1 dot 2, 3, 1 dot 4. Okay, so we'll call this the drive. So this is what the drive sees. So from least significant bit to most significant bit, the PLC, this, because it gets byte swapped, it's 0, 1, 0, 1. And so this is 0, 0, like that. And it goes along, and when you take this as a full 16-bit word, it gets messed up. So so this would be 0 through 7, and then 8, 9, 10, 11, 12, 13, 14, 15. And so that's where your bits are coming from. So like that's what byte swapping means. When you take it as a full word, which is these 4 digits here. You notice my actual status here is that 047F, and you take away the least significant bit, it becomes that 047E. So that's what that is. I know that was a ton of explanation for that, but byte swapping can get really confusing when it comes down to drive communications like this. And so yeah, that's why this value here is not at bit 10, sorry, bit 8. This needs to be at bit 10 on the drive side, but you have to break these up into those individual bytes. So I think that is quite a an extensive look at that, and yeah, I'm trying to think if there's there's much more before start to shift away from that. There any more questions just involved with this? Because wanted to shift over to a little bit more of instead of a technical conversation, because we're sitting at right at an hour, so yeah, that's pretty good. I might only be able to get to the next next topic instead of missing out on my baby introduction to indirect programming. And I know that's what Lucid has been wanting for so long, and I'm so excited to talk about indirect programming. So excited. Awesome, Michael. I mean, feel free to hang around, and we're going to be talking about more drive-based stuff, but it's really going to be kind of making a shift towards the PLC side. And Michael, for sure, like if you have any other questions, like just drop them in on the comments of this video, and I'll probably try to edit out some of this to make it a little bit more concise, but should have by the end of the afternoon a free Telegram how to build all this stuff, and kind of just what we went over, and a little bit easier, more concise. I think it's only like a 14-minute long video. So but yeah, so let's see, what was I, what, oh yeah, what I promised for, at least on the title. No, do not save program red winder. I'm gonna open up a different project, and it is a big project. Yeah, sure, we can save that. Yeah, while that's opening, it's a big project. It'll take a minute. Talk about fun stuff that I guess that we have going on in the world of Siemens. I've been introduced to more and more new hardware. I didn't realize that the S120 platform, the original hardware, I guess the first project I did with it, oh gosh, I don't even know if I want to say this, was back in 2006. And I think it came out even before that, and it's pretty much hasn't been updated yet, or not updated. It has had many updates to the hardware, but it's pretty much been the same thing, just like newer stuff. And like I was sitting with some of the Siemens guys yesterday, or I guess not yesterday, I guess it was Wednesday now, and talking to them about the new hardware, and it seems like there's some pretty cool stuff that's coming out. They got a new update for the CU320, so there's CU320-3, so a new hardware update to match the new CD motor modules. They have more CD motor modules, and then they're actually coming out with a new platform that is kind of the next generation platform of their drives. While they're obviously, since they're coming out with a -3 hardware for the CU, the current stuff isn't going to go away, but they're starting to introduce these newer drive systems called the the S220, and so it's like the newest, or the newer version of it, and so kind of looking forward to all of that. But some good stuff coming around the bend, more to talk about for sure. So what I wanted to talk to you today about in our PLC section was how to make a state machine. And on this channel, we've kind of talked a little bit about some of the way to program different things and how to configure stuff. And we have a couple of winders that use sequencers, and so it's step by step by step. And I've talked in some of those videos about how to program your motion control functions and everything. And you have to have some way to tell the drive what it needs to be doing. And in our winder program, it uses a sequencer because it's step by step by step. Well, in some programs that doesn't really work. And if you're familiar with what's called a state machine, is, let me pull up. I'll pull up what pull up a little paint. And we'll talk a little bit about what a state machine is if you're not familiar with it. If you are familiar with it, you can get some coffee, take a break, try to stretch your legs, try not to fall asleep with my like insomniac solution. Yeah, if you have insomnia, just turn on these videos. It'll just be great. It'll put you right to sleep. If it doesn't, then you're weird like me, and we should hang out. But let's look at what a state machine is. Is that gonna actually? Yes, it is. State machine. What a state machine is a way to put a piece of equipment into various, drumroll, states, meaning that each state has different wow, that's terrible, inputs, and set of outputs. So in each state, you are going to set all of your different outputs to some sort of configuration. So if this was a digital state machine, this might be like 0, 1, 0, 1, 0. And we could call this state 1. This is very basic stuff. State 2, the outputs. Same one. We have 5, 2, 3, 4, 5. Might be 1, 1, 1, 0, 0. Okay. And so forth for however many states. State N, because we are fancy, and it will have the same outputs. So, and what you have is you have your different states, and then you have your different transitions. So depending on what your inputs are, will cause a transition to either state, the next state, or state N, whatever. And these are, in a normal state machine, these would be shown like what the inputs that would cause a transition. So if you're in state 1 and your inputs do this, and something happens, you go to state whatever in. That's kind of what it is. And then it will stay in state N until you have another transition. So another move. And it's very subtly different than a sequencer, because if a sequencer just goes straight down the line, there's no real good way to go back up here. I mean, there is, but it just goes from step 1 to 2 to 3 to 4 to 5. Well, in a state machine, you can go from state 2 to 1 to N, anything in between, and anything in between can go to any other state. And so there's a very, very like powerful method about understanding this concept of state machine. If you have a piece of equipment that essentially is going to just be running, and I'm going to show you a little bit of the code that I have for a piece of our agriculture equipment. That it is a state machine. The equipment is a pellet mill, and what we'll do, Control A, delete, and then we're gonna draw the pellet mill. We've talked about this before, but it has in the front of it has kind of a die, and you shove stuff into the middle of it, and it squishes up through this, and there's holes in this, and it rains down little pellets, and then you collect them up in another bin, and so you have this big pile of pellets. That's what a pellet mill is. Very simplified form, but you have a bunch of stuff up here that gets shoved in, conditioned, and then gets shoved into this pellet mill. It spins and creates little plugs of pellets. These can be these can be wood. These can be fertilizer. These can be really whatever. Corn, dog food, anything. And they're used all sorts of places. The pellet mills are everywhere, in tons and tons of places in agriculture. So what I'm going to do is we're going to switch over to now to Portal, and I've actually brought up the program for a pellet mill system, or it's a full plant that is, I don't know if they're actually currently running today, but they are running, and they produce fertilizer pellets. And I'm going to show you a little bit of how to set up a state machine and why it is a good thing to use for this application, at least in my opinion. If you don't agree, feel free to comment, and we can talk about the nuances between controlling things in a different way. So let's go here. Not that one. Need to go to. I'm going to show you, and this is a little bit about each section of this plant is broken up into zones, and each zone has controls for it. And here is our pellet mill control. And if you notice, if you're familiar with the channel, if you're familiar with Siemens at all, you notice this is in a library. It's locked up. It's perfectly safe. And if you're not familiar with how to do that, I think we have covered that quite exhaustively in a lot of different ways. But just know that I have a library that I can pull in, and if I were to make changes to this and update that library, I could just open that library in a different project and just drag this code. If the library was already in the project, I could click update library and it would update the code in this. So really cool library functions, but that's for another video. We're talking about state machines. So one of the things about a state machine is it has states, right? Well, the most important thing about a state machine is keeping up with the actual state. And in this one, the mill state is an output of this block. And the reason I put it as an output is so that if you use this, because we're doing a plant in Indiana that has, starting off when they're starting up the plan is to start up 5 pellet mills and expansion up to 8. And so I want this code to be really good and modular, so that really I don't have to don't have to make 5 copies of it. And if I make a change, make changes in 5 places. And so the mill state, though, not only does it determine what the machine is doing, it also is a signal to our SCADA platform about what the state. So if I know what state of the machine is in, I would be able to turn on and off LEDs on a SCADA platform. I would be able to make decisions about, oh, hey, if it's in a state to where it's slowing down, then I know I need to correct for that on the input. Say, for example, I know if I'm in an overload state, maybe I might need to slow things down. If I'm in an underload state, maybe I might need to speed things up, something like that. And so that is what this mill state is. It also just, that's why it's an output. We could use it as a static, and there's benefits to having both. But in this case, that mill state is going to be what determines how the machine is running at any given time. Now, here's a couple of things. You would think that you have, if you are in state, of course I open up one that doesn't have anything in it. So if you're in state 50, which is auto stable, here is what it's doing. And so for every number, there's going to be logic associated with what the machine is doing at that state. So you have the states themselves, and then the transitions. And so let's talk just for a second about the state. Each state, for example, this overload state, it says if, and I'll talk about this overload update, this kind of update complete. We're gonna talk about all sorts of different stuff about this. But so if it's in this mill state 51, then it's going to be trying to slow down the feed, because if it's in overload, if it has reached a current that is outside of this threshold that we set up, it goes into this overload state 51. And so it has already transitioned into state 51. Now what's it doing? While it is in state 51, it means that it is in an overload condition. You want to try and reduce the load. So you're going to slowly pull back the feeder speed on this pellet mill. And so we're subtracting away the feeder step. We're subtracting that away from the feeder speed set point. Then we have some conditions to where to make sure that we don't slow it down too much, take it to 0, or even worse, take it negative. Like we have a minimum feed speed. So that sounds pretty basic. Same thing for an underload. Depending on how the machine is, where it is, like we have a warm-up timer, we have all of these things that kind of slowly ramps things in. If you've been running for a while and all of a sudden you're not getting quite enough load on your pellet mill, and there's reasons for that, then you want to speed up the feed a little bit. You want to try to load it up a little bit. And so that's same thing here. Now, you have all of these states that are the actual just states, and you have like from 50, 51, 52, 53, 54. All of these are running states. And then you have all of these transitions. Remember, we have, and I signify them as a little arrow. And so anywhere where it says and has an arrow or a state machine transfer. You have states and then state machine transfers, 0 to 1, 40 to 41, like all these different ones. So let's look at the transfer state of from 50 to 51. So 50 is our auto stable. So that means that everything's come up, it's running. 50 is where it wants to be while you're running in automatic. Well, how does it transition into the overload state? It's on this line, 50 to 51. So the first little thing that you have to do is, we'll talk about this in a second, but you have to make sure that you only have one change of a state per cycle. And the reason that is because if you don't do this, then you can have two sets of variables that change, and then all of a sudden you don't understand that it's swapping between the two. Because if you're monitoring things on a single update, it steps through all of this code, and by the time it gets down to the bottom, it's already changed states multiple times. So you want to limit the number of state changes to one per cycle. So that's what we're doing here with this state change active. And you have to determine, all right, when do I want this logic to be in effect? And so for this one, we set it to where it's, if the mill state is only in 50. So if it is running in auto stable, it can transition to an overload or an underload or anything. And the reason you want to do this instead of, and I'll talk about the numbering here in a second, that you want to make sure that if you're in an underload, you should go to auto stable first before you go into an overload. If not, then something doesn't make sense. But in this, if you're in auto stable and your current limit gets above a set point value, this like PM overload set point, you're going to time that out just to debounce it, and then you're going to initiate a state change. Okay, so one shot onto a state change, and it moves 51 into the mill state, and then it automatically kind of bumps down the feeder. You don't want to have to sit there and wait. If you hit an overload, if it triggers this, you want it to bump down. So that's what's going on here. But it sets this state change active because you would not want another state to overload that state change, or another transition to overload that state change, just by some fluke. And if it is, you would want to be able to see it. And the only way that in the trace function you would be able to see it would be if you're using this sort of logic. So triggers a state change that prevents anyone else below it from changing. And then at the very top, you are, if there's a state change active when it comes into the cycle, you're going to reset it. So that means only one state change per cycle. If there's not a state change active, then it doesn't matter. So like you're not resetting. One thing also that you may not realize is if you use just a regular coil, it locks that bit to where nothing else can change it. But if you use a set or reset bit, it turns it on. And even obviously a set bit, if it comes on, the bit will stay on even if the logic going up to it goes off, until a reset turns it off. But you can have multiple sets and resets, and it's whatever the last one that gets fired, that's the one that stays. So you can, inside a group of logic, you can set something up here, use it, and then reset it down here, and it's only set in between that logic. So you can kind of get some goofy stuff when you're doing these using set and resets. But also at the same time, if you were trying to change a change a value, change something, then, and it's not changing, then you may have a regular coil somewhere that's overriding it, and it's kind of locking it out. And it's whatever that last coil is, that's the only one that's ever going to get updated. So anyway, so we got that state change. And so that's how you're doing this. You're going from one set of configurations to another set of configurations based on what the state is. And the way to think about these are, you can go through and look. I try to group my states and everything kind of logically, because I know that if I'm in auto, I want to be able to go to, I know I want to be able to go from into overload, underload, recovery, clean out, all of these different states. And then you just kind of systematically go through each state and say, okay, is there ever a time that I would want to go from, say, the underload state, which is 52, is there ever a time that I would want to go from this underload state to auto, so state 50? Well, obviously, yes, you would want to have a 52 to 50 transition if in an underload, like if your current is able to build back up, you want to go back into auto stable. You want to be back in that auto run. And so there is a 52 to 50 underload to auto stable transition. And all it's doing is, if it is in underload, then it is, and it's that torque, the current goes above it for this little timer, it triggers a state change and just moves it right back in to auto stable, which is state 50. And so that's the basics of a state machine for this. And then as you go through, the first pass of this, I had an overload and underload. So I knew I wanted an auto, so an auto stable. So that's where I wanted it to be. And so one of the things about picking the numbers for the state is you want to give yourself numbers above and numbers below, because you can do some tricks. Like, for example, I have it's called a PM stalled. Okay. So if at any time that you are running in auto, that the pellet mill motor, the main motor itself, gets these warning codes, it means something's up. It means that it's running into this situation to where it's starting to stall. The pellet mill motor, it's a G120 running in vector control, but it's not running in vector control. It's a vector control drive, but it's only running in volts per hertz for reasons. Like, it just works better for this application. So meaning, because it can't actually detect the speed, it has this stall detection system that puts up a 7409 or a 7805 that it starts to warn it and say, hey, something's going on. And in that case, I want to immediately, you have just a few seconds to be able to kind of recover in this. And so immediately I want to cut stuff. I want to cut stuff out. I want to change into this stalled state and quickly recover. It's not an overload state, because an overload kind of just ekes stuff down. A stalled state, it's not like a physical emergency, like something's about to break, but in order to keep running, you have to make quick changes. So it's a different kind of state than the overload state. Anyway, all that to say, any state above 50 gets this treatment. And if you notice the logic here, that logic is designed because every number above 50 means that it is running in automatic. And so as long as we're not in that stalled, it's already transitioned, because remember, this is a transfer. As long as it's not already in the stalled state and it's above 50 or 50 or above, that means it's running in auto. That means that there's no person sitting there operating this machine. And so we want to quickly do that. The only way that you can do this is because you sit back and you say, okay, I want my base automatic state to be something. Anything below it, there are other states like manual mode, manual control, that, or recovery states, anything. There's all sorts of states that are not in automatic that tell somebody or tell the machine that either A, someone is operating the machine manually, or it is starting up and you shouldn't act as if it is running, it's running in a stable state. And so that's why you put 50 there. If you have a more complex machine, maybe that number is 100, maybe it's 500, because maybe you have a lot of steps in between, that a lot of granularity. There's really only like there's really only like 2 things that you could change on a pellet mill in terms of like while it's running to make changes. So that's why I said, okay, 50 states is probably enough. There's only 4 motors, and so that's only 4 combinations really that you could have of, not 4. There's only so many combinations you can have that's like valid states of those motors, and then that's it. And then so that's why I picked 50 on this. If you have a machine that has like 20 or 30 valves, or something that has a lot of different possibilities for combinations, then maybe you want to have a state, like a stable state of 100 or 500 or something like that, to give you those above and below. Couple of things about all of these is, one thing that I do is any fault state is a negative number. And the reason I do this is because I can easily say that if your mill state, and if you notice this, if my mill state is anything 0 or above, that means that I'm internally, from my logic, says that it is okay to run. And so that's what this internal permissive. And if you notice, because I'm using that standard coil, that is the only place that it's going to be able to operate. Like, it's locked out. There's no other place that can override that anywhere else. And so this little bit of logic, because if my e-stop, if I don't have my e-stop, I immediately throw in a -2, and I can't control anything else. Like, if I don't have an e-stop, nothing else can change it, because nothing else can do anything if there's a negative number on the mill state. And that's the logical way of saying, all right, if there's a problem, then I can't like automatically do this. And I'll show you, this lockbox is a pretty cool little thing. There's like a physical key that if you want to open up the front of the pellet mill, you have to have this key. And the only place where that key can reside is in another lock that has this lockbox control in it. So you have to unlock the key to like physically release the key in order to get it to walk over to the front of the pellet mill to unlock this front thing. And what that does is, there's this lockbox state that the second that you turn that key, it locks out the machine, and like tries to, if the machine is running, it will fully power down and like grind it will put it to a stop, not let it just spin free. It will actually slow down and put the brakes on in order to stop the pellet mill motor as fast as possible. And so that's what these are, and that's how I do this. And it's also, the reason I use like a negative number on that is simply you can take a piece of logic and say if my mill state is negative, then it's in some sort of fault state. It cannot run. And so you can flash on a screen like a SCADA flash or something like that. Like that's what this can be doing. So yeah, that's a little bit about that. Trying to think of. So yeah, here is the kind of state 30, which is kind of this auto startup that you go through this. You kind of go through these steps, and it starts to feed in stuff. And so while you were this state 30, let's find where state 30 is set. Da, 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 da. I can't remember where it is. But this auto startup is if you were in anyway, there's a lot in here. Anyway, so if you're in this auto startup state, this is kind of what it's doing, and it's going through and just waiting for all of the motors to kind of kick on and go. And so if you're in automatic operation, you have your internal permissives, you have your pellet mill permissives, you have your permissives. So those are actual physical buttons, inputs into this logic, and you're not in automatic shutdown, and you click a button that says, hey, I want to start up in automatic. It starts to go through all of this and slowly steps through everything to where it starts getting everything moving and going. And here's some things though, like all of these states that are less than 50, you don't get the benefits of having all of these other transitions like overloads and underloads and stuff. And so there's a little bit of stuff there that, like, say for example, if something happens and you shut down before it's stable, you need to go back through and start resetting and stopping stuff and like flipping bits and stuff. And so the most difficult part of a state machine is your transitions, but then if something doesn't goes correctly, to make sure that it gets reset into a way that can be recovered from. And the worst part on this state machine was before auto stable, because once it gets into auto stable, once it gets into state 50, everything's running pretty well, and then it has a pretty well defined way of shutting down because it's running in automatic. You don't have somebody turning on and off random stuff. Like, it's running. So in this case, I ran into some problems with if it didn't get started up in automatic and stuff was on, like a couple of the motors would be on, but it never got into that state 50. That's why you see a little bit of like junk. So like these setting and resetting. So like sentry run, sentry stop. So like if you hit the stop button before it gets into that 50, you hit that stop button and it's less than 50, then it puts on all of these, and then all of those need to be reset. So those are the difficulty things. That whole concept, that whole like thought process between a state machine versus a sequencer is subtle, but it's very wide range, and it's kind of like separate worlds. And what's crazy about both of them from an outside looking in, they kind of seem the same. You have one number that tells you where, like, what place you are in. And in a sequencer, you would have a sequence step 1, 2, 3, 4, 5, and it's expected to kind of go along just 1, 2, 3, 4, 5. The problem that comes in with a state machine is it's not always linear. Like you can get to a 50 and then you can go to a 54, then you go back down to 50, you go to 51, you go to 50 again. Whereas with a sequencer, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That's how it's designed. So, a couple things, just like we'll show real quick. If you notice on these like these states here, I have these auto stable 50. Okay. Auto overload, auto underload. Those are all variables, but it just shows 52. Those are constants. And if you're using a state machine, help yourself out and go through in your interface, set up all of your constants. So that instead of there just being numbers there, there's a variable there that tells you something. So in this case, idle state's 0. If you go into -1, it's going to be idle timeout. So that is, if it sits there in state 0 for I think it's 60 seconds without the machine starting back up, you actually have to go in and hit reset, hold reset, and then reset it out of a fault state in order for it to come back up, because you just don't want somebody accidentally coming in and changing a screen or something and it start up the pellet mill. You'd hate that. So that's what that's trying to prevent. But so there's all these other oiled timeouts and stalled PM and all these different things, and there's all these different states that could go into the state machine, and instead of just being a number, they're an actual variable. And so yeah, and that's how they show up. They show up as hashtag blue number or blue variables, or maybe teal variables, whatever it is. Yeah, blue variables and then teal numbers, and it tells you the numbers. Help yourself out and just do that. And when you're like playing around with it, you might want to go through and think about at first your states that you're going to be using and go ahead and make constants for them. So as you are programming and as you are making these different states and these different changes, you're not having to remember, was 51 overload or was it underload? Was 54 installed or what? My brain can't handle it. Yours might be able to. I should hire you. That's what I should do. Yours can handle all that. But no, so that's kind of it. I think for what I was wanting to kind of go through on the difference between a state machine and a sequencer. Let's see, is there anything else on here that might be interesting? Nope, I don't think so. Oh, I will say this. Like manual operation, that's just a way that's like if anything is running and it's not an automatic, and it's not it's not in like some fault state, then it's in manual operation. And so like that's pretty cool. I'll show you one thing. What you can also do with this is, because of that state, I'll show you on an HMI. There's a couple in this project. Let's just look at the main control room. Show you how easy. Actually, that's not what I mean. But so how you can tie your state into a state machine. Let's bring that to the bottom so we can actually click on this. Control 5 to bring up our inspector window. So we've clicked on unknown state, or not unknown state, but this is a symbolic IO field. If you're not familiar with what that is, we could bring this over here. It is a symbolic IO field right there. You drag that in, move it around, change it. But under its contents, we're using a text list. So it's symbolic IO field text list, and what this means is it is going to be looking at this tag, and if you'll notice, that's the name of that data block, and then db mill state. Another way that we could do this, since we're in Portal, we could go to our instance data block, which here is going to be that. And because we know it's an output, we know it's going to be somewhere around here, right? It's probably going to be on the bottom, maybe? I don't know. And I'm just using the detailed window. Could be right here. Mill state. There we go. And then you can just take right here and drag this over into here. And if that tag was not already made, it would make it for you. It would make that connection. And so that's how you use the detail window. Just select your data block, detail window, drag it over, drop it. Now, this text list, remember, your mill state is just a number. And so let's look at this text list in our HMI. Blah, blah, blah. And it should be, that's not it. I missed it. So it is under text and graphics list, blind. And the way you use these is you create a text list with essentially, Control 5, essentially all of those constants that you made over in your function block. And so here I know that even if I'm in like a state 15, because originally when I was going to do this, I was going to have individual states for if the pellet mill was running, or if the feeder was running and the century was running, and then those all be different states. But then I was like, whatever. I know that anything under 30 is not automatic operation, because I had automatic startup as 30, and so anything less than 30, greater than 0, or I guess greater than 1, since 1 is stopping, then it's going to be some sort of manual operation. So I just grouped it all into that. And then auto startup, auto running, idle, which that's a state we didn't talk about. And then recovering from idle, auto stable, and then all the stuff we talked about before. I don't have a 53 in here. I just noticed that, or a 54, which is the stalled PM stalled state. So I probably need to add that, but I'll probably do that another time. So, we are at about an hour and 45 minutes into this thing, and we've had a great conversation about the contactor control. Great interaction with the community on this. And as always, if you have a question or topic you would like to have covered in one of these live streams, comment. And really, I go through all of the different videos and everything, and I scour through the comments and try to collect up all of the things that I've missed through the years, or through all the videos. And yeah, so if you have some random topic, I am not afraid to admit if I don't know about it, and I will comment to that effect. But I also like learning things. I feel like I've been challenged to kind of do some topics and things from on some things like SEL and statement call lists, and and while I know that stuff, I don't do it well, and so that probably means I need to teach it, right? And the best way to learn something is by teaching it. And so yeah, I may talk just a little bit more about some other things here in a second, just kind of an introduction to the indirect addressing. Back behind the scenes, I'm pulling up the other version of Portal that I need for this, because indirect addressing can be very powerful. And in a couple of my videos, I've touched on some of the things that is used in indirect addressing, but I haven't really gotten into it very, very deeply because honestly, it can get you into trouble. And not saying that if you're watching a YouTube video that you don't know what you're doing, but there's a bit of complexity in indirect addressing that can really get you into trouble if your experience is from YouTube. And there are a lot of pretty complex systems out there that that are like, a lot of times you'll see them in like manufacturing facilities. There is one plant in Tuscaloosa where I grew up that the entire line is written in indirect addressing, and there is one person one person that their last name is Watts, but it is not, their first name is not Jason, that is the person that can work on that machine, and that person does not even work there. They are contracted out solely if there's any problem on that line, that he's the only one that can work on it. And he didn't write it, and it was written in German, and a lot of statement calls, so like essentially assembly language and indirect addressing, and it is incredibly difficult to troubleshoot. But once you get it going, it's great because it's super flexible and super kind of yeah. So a little history. The reason why Siemens really got this bad reputation back really in the late 80s and early 90s was because Alan Bradley invented ladder logic, and while Siemens processors could use ladder logic, most programs that came from Germany used structured statement calls. So it's essentially assembly language, and it's rough. And most of the stuff that came over, because you're using this assembly language, it kind of immediately helps out if you're doing indirect addressing, and so you're using a bunch of pointers and stuff, and it's real easy to do it in statement lists. But yeah, and so anything that came from Germany in the early 90s, or really it's probably even now to a big extent, would be written essentially in assembly language, and it's incredibly difficult if you're not used to it. And a lot of it's in indirect addressing in a lot of these German plants. We have a Mercedes plant in Tuscaloosa, and it's most of their the Siemens PLC stuff is written in indirect addressing, and so written by Germans. And anyway, all that to say, you get yourself into trouble if you're not careful and you're trying to go back and trying to fiddle around and fiddle with stuff on a running line. The worst thing you can do is make things worse. I guess the number one rule is, when you're trying to get out of a hole, is to stop digging. And if in a production downtime situation, that cannot be understated. Don't do something that's gonna make it worse. Like, don't make things worse if you're trying to get things back running. And honestly, this indirect addressing, you can quickly make things worse, really by just a change of one letter, one number. It sounds crazy, but you can accidentally change one number, accidentally delete a DB, and all of a sudden nothing's working. So, not to be doom and gloom, we're all smiles on this channel. But let's kind of talk about the concepts of it. So is um, indirect addressing is essentially using a pointer or an index to take blocks of memory, and instead of using specific addresses, specific places, you're just going to say, I'm going to use an offset from some pointer. Now, depending on what's getting put in there, you're just hoping that it's the right thing, right? And it sounds like a super complicated thing to do, but it actually can make things pretty elegant. So we just went and talked for about 45 minutes about state machines. And the code that I'm about to show you is a machine that it's a beer keg washer. And it have a local brewery that was needing a keg washer. They were scaling up their equipment, and they were gracious enough to let us build them a prototype. And in it, you have a bunch of valves to where you're flipping different chemicals and water and kind of moving around in order to clean out these beer kegs. And it sounds like the perfect idea for a state machine, because you take a state of the keg washer, and it's really just a configuration of a bunch of valves and whether or not a couple of different pumps are on. And then you run those pumps for a few seconds. You keep the valves open for so long, and you just kind of delay, and you just step through a bunch of states. So it's almost like a combination between a sequencer and a state machine. And I'll be very honest with you. This is the perfect application for this kind of like baby indirect addressing. And when I wrote this program, it was the first time that I really dug into this type of work, and it kind of blew my mind and opened up like a huge realm of possibilities for me. Going back and looking at it now, I kind of shake my head because I violated a lot of the rules that I teach you guys because of naming schemes and how to bring in stuff. So as we go through this, I'm going to show you what's going on, but then I'm also going to make a comment to you and myself. This might be one of the few times that my past Jason might be able to learn something from present Jason. So what this machine does, and it has essentially, you have a data block, not the right one. You have a data block of things called cycle storage. And a cycle storage is the way we designed this keg washer is it had two sides. So we wanted to be able to operate and wash two kegs at the same time, independently, and not just two kegs at once, but you could be operating one keg on one type of cycle and then operating a different size on different program, different cycles. So that was the intent of this. So you essentially have two machines in one, and each machine has a valve configuration for steps, and then you step through valve and pump configurations. So what you do is you say, all right, I want to run this cycle, which is a configuration of, it's a sequence of configurations of valves and pumps. And so I'll show you what that is. And you load a cycle onto one side of the machine, and then you run that cycle. You can load a different cycle onto a different side of the machine. And this machine we set up to where you had 10 possible cycles, custom cycles, that the customer could program themselves. So they could go through and set up at this step along the way. I want this configuration of valves. I want this configuration of pumps, and waits this long, blah, 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 all of this, and steps through those cycles, and it's completely configurable. And so we have 10 cycles, and here they are. So Each one of these machine cycles has a array of steps. So we have our step is an array of these I don't know what, I can't remember what ABW said, but it was step configuration. So in each one of those steps, so 0 through 31, we have up to 32 steps per cycle. So each cycle gets 32 steps, up to 32 steps. Each step has whether or not you are going to use that step. You have a valve configuration, which we'll talk about here in a second, a pump configuration, a start delay, an end delay, and a hold on complete. Meaning how long to wait to start everything up, how long to wait after you've finished all the configuration, and then whether or not you're going to require the user to hit that start button after this step. That's what those are. Valve configurations and pump configurations, those pretty straightforward. It's another data type, our valve config, that has all of our different valve configurations. And the cool thing about this is we can use this, and if on a different machine, we would just need to change this data type and change it to adjust how many valves, and we would still be able to use this. We'd have to reconfigure the HMI a little bit, but we'd still be able to use this, and I'll show you why. So all it is our program essentially goes through and reads these variables out of here, and it's just picking a step, it picks a configuration, and goes from there. And now, actually, that's pretty straightforward. Getting into the actual code, I'll be honest with you, I haven't worked on this in so long. I was working with it a little bit before to remind myself, and that's why the stream started a little bit late on this. And so let's go into our actual, let's dig in. And here's where past Jason wasn't as knowledgeable as present Jason, and so I'd probably do things a little bit different. But we just have a right side and a left side control for manual and automatic. I believe that's basically all it is. Yeah, we have some other stuff too. Like, don't worry about that other stuff down there. And if you notice, some of the rules that past Jason have broken, didn't name his PLC, didn't name his HMI. He hasn't commented each one of his networks. Shame on you. But I joke, but those do come a long way. And again, this was probably 6 or 7 years ago that I wrote this, and so I realize more and more every day that doing things the right way every time really does go in. Let's open up one of these instances of this machine cycle control, and we're gonna get into where things will start to get more and more like indirect addressing. Because remember, all of our data in our cycles are in all of these arrays. We have our cycle storage. Our machine cycle is an array of 10 cycles. So there's an array. And then we have, inside each cycle, we have an array of steps. So lots of arrays here. And we can think of about an array as just memory location. And we're going to look at something here. So we are passing in our current cycles, which is, just think of it as when you load in into your current cycle, that's picking out of that memory, or out of the cycle storage database, So either 0, 1, 2, 3, 4, you're just loading in, hey, I want to run this cycle. And all it is just a variable. Um, and you're going to run this in, and that inside of this machine cycle control block is actually going to be used as a index for a lot of things. So these are like start, stop, that sort of stuff. But where we really get into it is we're going to use this sort of stuff. So what's going on here is for each step, we have to have a delay. Remember, so this is the in delay timer. So this is the advanced step internal to this block. We're going to advance the step. And so it's going to move on to the next step. Well, we have an in delay timer. And so in order to access that in delay, and here's where past Jason didn't do this right. And the best way to do this, so past Jason referenced this cycle storage dot machine cycle, and then it used the current machine cycle, which if you notice, that's a hashtag. It's got the hashtag. So this current machine cycle, so that already one index. So cycle storage dot machine cycle, cycle storage is not the correct one. Cycle storage dot machine cycle is going to reference one of these values here. And instead of using 0, 1, 2, 3, we're going to indirectly address it, or we're going to go here and create a variable. We're not specifically referencing one thing, we are indirectly addressing it. So we go into, and remember the second, so step is an array of steps, remember? And so we need to burrow down into where we need to be in order to extract this in delay time. And so at step.index, this index is something that's in here that is a static variable that we are using to increment through each step in our cycler. And so look at how this is. It's creating an index, so an array inside of an array, and it's creating these indexes, and that's how it's using that. And so nothing is changing in this code, but depending on what is in these different arrays, that's what's going to be referenced, and that's what's going to be used. Now, I'll tell you, I did something wrong, and the best way to do this, because this function block is not a totally multi-instance function block, because you don't see a hashtag in front of this cycle storage, because I'm actually directly referencing this function block. No. XX. The problem is I didn't realize the best way to do this when I wrote this code. But the best way to use this would be to use an in-out parameter. And I have a video where we talked about using these in-out parameters, and this is one of the best places to do it. I didn't want to bring that up in that video because there's so much more about indirect addressing. But if this cycle storage was a in-out parameter, and then outside in main, when I called this, I actually tie this cycle storage into that parameter, then voila, it's completely reusable. Because at that point, you are going to be taking a pointer to a data block, and the pointer is going to be referencing the data in that data block. Now, I've said multiple times that this is kind of like indirect addressing light, because technically I am still using a data type here. that makes sense. So inside of what I'm using here, I have these data type pump controls. Sorry, not that one. I saw it a second ago. I'm technically having to use the different data types, and the reason why I did this this way is because I didn't understand the whole meaning of the data types. If I'd have brought this in, I would have had a data type of this step index, all of these custom data types. Okay. I'm still using indexes to index to the different arrays. The difference between full on indirect addressing is that instead of having a fixed data type, you were just going to be using offsets and pointers. So meaning that this data block could literally be anything. And either the programmer knows that you are putting certain type of data in, or there is some way to tell the program how much data is in there. In my case, I have a fixed array size, so I know the array size. Well, in indirect programming you're using indexes, but because it's a pointer, you will start at a certain place, and then you, instead of writing cycle storage dot machine cycle blah 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 index in delay, you're just going to use that same indexing scheme, but you're going to start at a pointer and then index down so many words and then use that as something. And I'll tell you that indirect addressing done this way is one of the most difficult, mind-numbing, mind-breaking, soul-crushing ways of troubleshooting, because that index could change inside a function block, and all of a sudden inside of one cycle your reference changes from here and it says, oh, okay, just go ahead and jump down 4, and then it runs the same code. And you can't see it. you can't see it because that index for like a trace function is only being updated. Yeah. So this is just a little taste of how confusing indirect addressing can get. These are just indexing some functions, indexing through arrays. And it's fairly simple once you understand the structure and you're like, okay, I have arrays of these data types, and I'm going to, instead of typing out cycle storage dot machine cycle 0, which would be machine cycle 0, I'm gonna create that 0. I'm gonna make a variable, and so it's still variably moving through stuff, but because you are using these data types, it makes it easy. Next time I might maybe go into another program if I can find a good program that I'm mentally able to process through. But yeah, shoot some questions about this. I know that this last little thing I blew through in like 20 minutes, but this is just kind of a little bit of an introduction. Think about it, make some comments, and yeah, that's the wrong one. The indirect stuff, the indexing and all this stuff. There's some other videos that show how to create pointers, because it's used in like the read data record functions. There's also a pointer that's used in DPRW and not RW, DPRD and DPWR. So like reading and writing, like DP, like the consistent transfer, those are all pointer based. And so if you want to learn a little bit about pointers, check out my video on the read dat. So yeah, the read dat and the DP read and write, and both of those use pointers. You can kind of like look in there and how to create those and kind of start mentally thinking about it. Then come back onto this stream and comment about questions that you have. But yeah, that's gonna be it for today. My head hurts. I don't know about you guys, and it has nothing to do with a closet door hitting me in the face this morning. It has everything to do with the cool stuff that you could do with Siemens. Hopefully, this has been a helpful stream. Hopefully, if you're watching this on demand, that yeah, hopefully you've learned something. Next week, don't know what we're doing next. Should have a couple videos coming out before then. I'll clip it up. I might have like, I don't know. There could be like 6 videos that come out next week. So be sure, if this has been helpful, like it, subscribe it, and ring the bell in order to be notified next time I get on. I'm going to keep trying to do these on Fridays, probably 11, 12 o'clock Eastern time. That seems to be good. We had 5 peak viewers. It's kind of crazy. We're growing, and you're part of it. And so I really appreciate you growing with this channel, and hopefully your world will be getting better out from it. I know mine is. And until next time, yeah, y'all have a good time, and yeah, don't work too hard. Go to the beach. Go to the beach like me. I'm gonna find a beach. It might be I don't know. It might be like in my backyard. I might just go get a sandbox and do that. But anyway, yeah, you'll do that. I'll see y'all. Bye.